This talk in the Building Minds with Patterns series is about the regulation pattern. We will briefly highlight the features of a generic cognitive architecture and discuss design patterns for cognitive systems. Then we will talk about regulation and delve into the specifics of the regulation pattern. And finally, we will review some cognitive systems having this pattern. What is a cognitive architecture? A cognitive architecture is a design for an artificial mind. It is realized in a diagram depicting the elements of the mind that the architects claim are necessary and sufficient to support thinking, or cognition. But how do we build such a system in the first place? The answer is simple. We need to establish a list of requirements identifying what the artificial mind will do. Once these requirements are elicited, we can then design a cognitive architecture to fulfill the requirements. So at a very high level, some initial requirements could be: 1. We want an artificial mind to communicate with a device, such as a car, a robot, a smartphone, or an avatar, that is situated in the real world or in a virtual world. 2. The device will send data, we can call this data observables, from the world to the mind, and receive commands from the mind. We can call these commands actuations. 3. Some components will think about the observables and infer new information about them. We will call these coordination components. 4. We will need to have the system learn and improve its behavior over time. The system will therefore need to observe its own performance. We will call these components that reflect upon the system's behavior reflection components. 5. We want the system to stay within its capacity for memory and performance and not get slower over time. So we need to periodically consolidate the information stored in the system, and therefore we need components for that. These 5 basic requirements can be supported in many different architectures. We now present a generic cognitive architecture template. In essence, a cognitive architecture is a blueprint for an artificial mind. Here we see areas for observation, coordination, reflection, and consolidation, as well as a device situated in the world. In this template, we can see a device situated in a real or virtual world. This device communicates with a cognitive system through observation components, which store input from the device into the system's memory. The observation components are also responsible for communicating with the device's actuators, which perform actions in the world. We also see there are coordination components which update the memory with new inferences. The reflection components are responsible for changing the overall behavior of the system. And finally, the consolidation components are responsible for ensuring that the memory does not exceed its available capacity. What are cognitive system design patterns? Isaiah Berlin once said, "To understand is to perceive patterns." In building an artificial mind, it's helpful to start somewhere, and preferably not from scratch. There are a number of cognitive system design patterns which can be used to implement the required mind functionality. Mapping requirements to design patterns can assist in defining the overall mind architecture. Some design patterns are depicted here. This talk's focus will be the regulation pattern. What is regulation? The noun regulation and the verb regulation can be distinguished. The verb regulation means to control or manage. The noun regulation has multiple meanings as well. According to John Piaget, a famous child psychologist, regulations as a noun are adjustments made to a cognitive system in response to disturbances. Regulations take the form of constructs added to the cognitive system's mental structures. A regulation can introduce elements such as implicit negations, disturbances, retroactions, knowledge of objects, or knowledge of related actions into the mental structures that comprise an action. Regulations can be simple or complex. Regulations can achieve, maintain, or prohibit a state. Regulations can affect external objects or subsystems. Regulations can add retroactions or loops to an action in order to stabilize the action and form implicit negations. Regulations lead to compensation, and a compensation is a form of reversibility. As a verb, we can consider two forms of regulation, causal and logical. Causal or physical regulation modifies actions based on feedback. Logical regulation modifies ontologies or taxonomies in order to eliminate contradictions. Since logical regulation occurs mostly in the coordination design patterns, this talk will discuss causal or physical regulation. So we will start by discussing actions, otherwise called behaviors, and sometimes called rules. What are behaviors? For discussion purposes, the terms action, behavior, or rule are interchangeable. The term behavior will be used to hopefully minimize confusion. A behavior is a structure that performs one or more actions. The action of a behavior may be primitive or composite. Behaviors typically marshal an ensemble of primitive fine motor actions. For devices, these fine motor actions are called actuations. An action can occur in one or more modalities. For example, visual, phonal, tactile, kinesthetic. Actions are causal and often exert forces upon objects. Actions may also be recognitive, that is, used to recognize objects. We can imagine a chair recognizer action that recognizes all kinds of chairs. When faced with something that is chair-like, it will decide, yes, that's a chair, or no, that's not a chair. A behavior typically has three parts: a context, which indicates preconditions for triggering the behavior, one or more primitive or composite actions to be performed, and a result, which indicates the predicted or expected postconditions upon successful performance of the behavior. The context specifies conditions that exist in the current situation. Objectives are conditions that are desired but may not yet exist in the current situation. Typically, objectives appear in the result portion of a behavior, in that the objectives are predicted by the behavior. The actions to be taken may be primitive, which means atomic or indivisible, or composite, which means they contain other actions. In a constructivist cognitive system, a potentially infinite number of condition elements can be dynamically synthesized. They can be represented as numbers, usually integers, or literals, which are alphanumeric constants. The condition elements can also be negated to demonstrate the non-occurrence of a particular condition element. A behavior may also be reified, which means a condition element can be synthesized that refers to or represents a specific behavior. In non-constructivist cognitive systems, a finite number of condition elements, usually called tokens, are defined in advance, so that the behavior contexts and results are often simply lists of numbers or vectors of numbers or numeric tokens. In artificial intelligence parlance, there are two types of behaviors: policies and macro operators. For the most part, policies and macro operators are largely equivalent. However, these terms are favored by different artificial intelligence communities. The reinforcement learning community prefers the term policy, while the symbolic learning community prefers the term macro operator. Given a context containing preconditions P, not Q, R, a primitive action A, and a result containing postconditions x, y, such a behavior can be represented as either a policy or macro operator. Policies typically specify only the context and a single primitive action to be performed, while macro operators may specify the context, one or more primitive or composite actions, and the result. Behaviors can be sequenced. When one behavior follows another, they can be represented as chains. Policies often contain only primitive actions. Therefore, policy change show their contexts changing as the primitive actions are performed. Also, policies may contain negated objectives as part of their contexts. When macro operators are chained, the result of one macro operator becomes the context of the next. Macro operators, as their name suggests, can also be combined into composite macro operators. In an artificial cognitive system, some statistics associated with a behavior may track the number of attempts the behavior has had, the time frame in which the result should obtain after a successful performance, the number of times the behavior was successfully performed, the number of times the result was attained, and so on. These may be very different numbers depending upon the performance strategy employed. For example, if the result conditions are detected rather than asserted, then the result is correlated to the context and action rather than caused by the context and action. So, returning to the idea of regulation, there are two kinds of regulation: causal and logical. Causal regulation, or physical regulation, modifies behaviors based on feedback. Logical regulation modifies ontologies to eliminate contradictions. The remainder of this talk will focus on causal or physical regulation. To regulate something, we need feedback, and we receive feedback from the world. Causal or physical feedback can either be positive or negative, and expected or unexpected. Expected positive feedback is confirming. Expected negative feedback is disappointing, at the very least, or it can even be surprising. Unexpected positive feedback is serendipitous, while unexpected negative feedback is often said to be shocking. We use this feedback to alter behaviors. How does that happen? We alter behaviors through two processes: reinforcement and correction. Typically, when an individual repeatedly performs an action, she gets the same result. When different results ensue from performing the same action, we can say that the action has been regulated in some way. Either the action was corrected or it was reinforced. Reinforcement and correction are the tools of regulation. Regulating confirming feedback primarily involves reinforcement. Jean Piaget, a famous child psychologist, said that if an action succeeds, it should be used again in the future, and possibly generalized. The success is called positive feedback. Reinforcing regulations utilize positive feedback to generalize the situations under which an action may be applied. For example, if using a sad face successfully earned a child a lollipop from a parent, the child might use a sad face to get other items from the parent in the future. Most actions of an individual will not always be successful because the success conditions are not always known. In this sense, the action is incomplete or partial, since the unknown success conditions represent gaps in the action. For success, the gaps must be filled in, which requires the action to be practiced in order for the success conditions to be found. In this way, gaps provide positive feedback. Reinforcing regulations can allow the deficient action to be augmented through rehearsal, so that missing success conditions can be acquired. In other words, the positive feedback of the gap provides the opportunity for the action to be practiced, so that it can be refined. and reinforcement remedies gaps. Disappointing or surprising feedback is regulated through correction. If an action fails, it must be corrected in order for it to succeed in the future. The failure is called negative feedback. Obstacles provide negative feedback. Corrective regulations may remove obstacles, eliminate options, or reduce forces in a suppressive manner so that negations can be introduced and utilized. A corrective regulation may add negations to an action to prevent its execution or refine the conditions under when the action should be applied. For example, if a person falls and injures herself while running with scissors, she will learn not to run with scissors. Thus, the negation is introduced into the running action for the situations where scissors are involved. Regulating causal feedback through reinforcement and correction can occur in different ways. Altering the priority of behaviors is one way to regulate causal feedback. Reprioritization, therefore, is one action regulation approach. According to Sutton and Bartow, a population of policies whose priorities are regulated by a reward value are used in reinforcement learning systems to model the human cortico-basal ganglia learning mechanism. We can envision in reinforcement learning a policy selector whose job is to repeatedly pick the best policy for the current situation. It searches for the optimal policy that achieves a maximum future reward value at each time step. In value-based reinforcement learning, systems such as Q-learning, the policy selector learns from delayed rewards, and it estimates the optimal value function for any policy. In model-based reinforcement learning systems, the policy selector builds a transition model of the environment. The challenge in reinforcement learning is to select policies which maximize an extrinsic reward. That means a reward from outside the system. The problems with reinforcement learning are, number one, constructing a suitable reward function. Number two, reward values coming from an external critic within the environment rather than from within the system itself. And three, the reward function is usually tuned to a specific task within the environment and must be reprogrammed for different tasks. Intrinsic reward moves the critic from the external environment to the learner and often embeds an intrinsic motivation subsystem within the learner as well. The adjustment of policy selection based on the reward signal can be viewed as regulation. Reinforcement learning has been extended in several ways. Hierarchical reinforcement learning seeks to define a task hierarchy based on the possible actions of an agent in a given domain. Options are a looping formalism added to reinforcement learning to perform macro actions. A reinforcement learner is a Markov decision process, or MDP, if each action taken is conditionally independent of any prior actions taken, or situations achieved by the agent. MDPs can be viewed as random games with one player having a known, fully observable situation. When the situation is not fully known, then the agent participates in a partially observable Markov decision process, or POMDP. Semi-MDPs, or SMDPs, allow actions to be selected whenever a state changes, in continuous time with a probabilistic state duration. Hidden Markov models, or HMMs, can simulate hidden states and learn despite noise in the environment. Homeostatic reinforcement learning, or HRL, combines reinforcement learning with a notion of intrinsic reward via drive reduction. This approach models the operation of the human hypothalamic regulation system. It assumes certain actions maintain physiological stability by reducing deviations in a multidimensional space. Multiple reward signals pay off for returning variables to homeostatic target values. Homeostatic reinforcement learning assumes that the effects are immediate and short-lived instead of delayed and long-lived, and therefore the effects can easily be captured as a reward function. When reward is defined in terms of physiological stability, the reward function both maximizes reward collection and minimizes homeostatic deviations. Note that homeostatic control can be done in a Bayesian manner as well. Since neural networks can be trained to select appropriate actions for an input state, a feed-forward or recurrent neural network can represent a population of actions. Regulation through priority modification in neural networks involves changing the weights of the network nodes. Backward propagation of errors is a common method for training neural networks, and it is also used in Q-learning. So, priority modification is the first kind of regulation technique. Altering behaviors genetically is another technique. Genetic modification is a regulation approach where behaviors or clones of behaviors within a population are surgically mutated or combined. Weak behaviors in the population are eventually removed. To reinforce confirming feedback, raising the priority of a behavior to make it more likely to be selected in the future is one regulation approach. A corrective approach for disappointing causal feedback is lowering the priority of a behavior. A genetic approach to regulating confirming causal feedback is to recombine a behavior with other successful behaviors. And a genetic approach to correcting disappointing or surprising causal feedback would be to mutate the behavior. Once a specific behavior has been chosen and tested, the feedback received can be used to regulate the behavior. The priority of a successful behavior can be raised. The priority of an unsuccessful behavior can be lowered. Successful behaviors can be combined via chaining. This is the beginning of automaticity, when successive actions become merged. Successful behaviors can also be combined via crossover, where context and results are merged. For example, if eating cashews on some occasions gives you pleasure, and eating raisins on other occasions gives you pleasure, you may try eating cashews and raisins together. Negations can be introduced into the context of a behavior to correct it. For example, if an element H exists in the situation at the time before the behavior failed, then the element not H can be introduced into the behavior preconditions as a corrective regulation. For example, if a person falls and injures herself while running with scissors, she will learn not to run with scissors. Thus, the negation is introduced into the running action for the situations where scissors are involved. Mutation is a very important technique and is the key to the process of accommodation, which emphasizes cloning a behavior and then substituting its elements. What is the regulation pattern? Regulation is the modification of action based on environmental feedback. Regulation typically occurs via correcting or reinforcing modifications to an action. Action attempts, sometimes called trials, are sent to a correlator which determines whether or not the selected action has succeeded or failed. The regulator corrects or reinforces the selected action. Forces for using this pattern involve when actions need to be prioritized, culled, or adapted by environmental feedback. Here we have a device situated in a real or virtual world. The device emits percepts, urges, or propriocepts, collectively called observables. The perceiver updates the observables in memory. The perceiver creates a situation, which has the most recent observables. An actions selector chooses actions to perform. Objectives are conditions to be attained. Actions are macro operators or policies. An attempt is the action tried by the system. The selector sends the selected action to perform to the executor. The executor transforms the actions into its actuations and sends actuations to the device. An actuation is a command that the device understands. Device sends a proprioception indicating whether or not a specific actuation was performed. The performed actuation propriocept is forwarded to a correlator that determines the reward for the attempts made. A terminator determines if an objective has been achieved in the current situation. The terminator sends an objective achieved attainment signal to the correlator. The correlator then sends a reward to the regulator. A reward is feedback from the action attempt. Finally, a regulator reinforces or corrects actions based on the reward. What is a cognitive system? A cognitive system is a software and hardware implementation of a cognitive architecture. It is the instantiation of an artificial mind. There are a number of cognitive systems that have been researched extensively. Here is a chart of some cognitive systems and the design patterns they implement. Cognitive systems which have the regulation pattern are highlighted in yellow with a red outline on the cognitive systems chart. In order for us to study cognitive systems, we have to align them so that their elements are comparable. The characteristics among cognitive systems that seem important are the ability to perceive information from a device, the ability to be reminded of prior events and situations, the ability to create, retrieve, select, and execute actions. These general regions are depicted in the comparison template, and the cognitive systems we study will be laid out accordingly. In his book, Autonomous Learning from the Environment, Wei-Min Shen presented the Live system, which used rules as behaviors to form a model of its environment. Live employed a means-ends planner to conduct problem solving, an experimenter component to conduct experiments to identify causes for failed behaviors, and an explorer component to ascertain consequences when action effects were unknown. When a behavior fails, a regulation module called the revisor splits the behavior into two new behaviors by adding discriminating conditions to the behavior context according to the complementary discrimination learning algorithm, or CDL+. Also, goal interaction and sub-goal looping are detected by the planner and spur further behavior refinements. In the absence of relevant behaviors, Live takes an exploratory action and uses the state changes of the environment to form the context and result of a new behavior. New relationships among condition items are also synthesized. The experimenter module conducts experiments to repair behaviors. A behavior is selected and instantiated, and the context preconditions become a system goal. Once the preconditions are attained, the behavior action is taken. If a prediction fails, the experiment was deemed successful, and the new information is used to augment the behavior. Otherwise, another experiment is conducted using a different instantiation. The Live system uses many genetic modifications to regulate its behaviors. Clarion is a cognitive architecture developed by Ron Sun and Associates to perform decision-making, reasoning, and inference using motivation and emotion. The system simulates tasks and domains in cognitive psychology. The metacognitive subsystem in Clarion functions more like the metacontrol design pattern that monitors other components in the system. It also adjusts rules and thus performs as a regulator according to the regulation design pattern. Therefore, Clarion partially matches the regulation design pattern. The latest iteration of the cognitive system has been augmented with various large language models, or LLMs. Regulation is also related to the notion of plan repair in case-based reasoning systems. In this case, an action corresponds to a single plan with preconditions, steps, and effects. The Chef system by Hammond produced recipes and simulated the steps of the recipe. It retrieved plans which initially satisfied as many of the recipe objectives as possible, and modified the plan to fulfill the remaining objectives by adding ingredients and cooking steps. When a plan failed, Chef formed a causal explanation for the failure and used the explanation to retrieve and apply repair strategies that could correct the failed plan. Each repair strategy was a specific regulation that genetically modified the plan. All applicable repair strategies were instantiated using the causal explanation. Then a decision component selected and applied the best repair strategy, thereby generating a new plan. MetaDharmok by Antonon and Associates is a case-based planning system that plays Wargus, a real-time strategy game. The system accepts advice from a human critic. The system uses failure patterns to detect anomalous behaviors and learns from experience which failures are salient enough to address. This system is a partial implementation of the regulation pattern as plans are modified in the case space. A human advisor suggests the initial plans to use. So to recap, the regulation pattern modifies actions based on environmental feedback. Action attempts are sent to a correlator, which determines whether an attempted action has succeeded or failed. The regulator corrects or reinforces the selected action. This pattern is useful when actions need to be prioritized, culled, or adapted by environmental feedback. You can read more about this design pattern in the book Building Minds with Patterns, available on Amazon. If you found this information useful, please like the video and subscribe to the channel, and visit us on Patreon. Become a member so that we can bring you more helpful content. Find us on the web at Linktree. If you need advice on systems you are building, book a consultation on Calendly. We'll see you in the next video.